This research paper addresses the challenge of deploying reinforcement learning (RL) in real-world scenarios, focusing on safe RL and offline RL. It highlights the limitations of existing safe RL approaches that mainly target online settings and may incur risky constraint violations during interactions with the environment. The paper introduces a novel offline RL solution called Trajectory-Based Real-Time Budget Inference (TREBI) to tackle the real-time budget constraint problem, which requires the deployed policy to adapt to dynamically determined budgets without retraining. TREBI approaches the constrained policy optimization problem from the perspective of trajectory distribution, allowing for the derivation of the optimal trajectory distribution with respect to a certain budget and a given offline dataset. This method ensures strict constraint satisfaction in the trajectory level, which is crucial in safety-critical domains where a single constraint violation could lead to catastrophic consequences. The proposed approach has been tested on various simulation tasks and a real-world large-scale advertising application, demonstrating its capability in solving real-time budget constraint problems under offline settings. The paper also provides theoretical support by proving an error bound of the estimation on the episodic reward and cost under the offline setting, thus providing a performance guarantee for TREBI. In summary, this paper presents a significant advancement in safe and offline RL by introducing the TREBI method, which can efficiently handle real-time budget constraints and ensure strict constraint satisfaction in trajectory level. This research has implications for various real-world applications, particularly in safety-critical domains, and contributes to bridging the gap between complex research papers and concise summaries for expert audiences. Safe offline reinforcement learning with real-time budget constraints is a challenging problem that requires learning a safe policy from static datasets while satisfying budget constraints. The authors propose TREBI, a method that adopts the diffuser, a trajectory optimization method based on the diffusion model, to model the optimal trajectory distribution with respect to a certain budget. TREBI approximates the trajectory distribution of the behavior policy using the offline dataset and achieves adaptive responses to real-time budgets in the inference phase. The authors theoretically prove an error bound on the offline estimation of the episodic reward and cost, providing a performance guarantee for TREBI. This method differs from existing safe offline methods in that it solves the real-time budget constraint problem in the trajectory level with strict constraint satisfaction. The problem of safe reinforcement learning with a budget is formulated as a constrained Markov decision process, CMDP, where the goal is to learn a policy that maximizes the expected cumulative reward while satisfying the budget constraint. The authors discuss related work in offline reinforcement learning, safe reinforcement learning, and safe offline reinforcement learning, highlighting the limitations of existing approaches, such as primordial methods that can be sensitive to initialization and learning rate, and the need for new approaches that can handle real-time budget constraints. Safe offline reinforcement learning with real-time budget constraints. The problem of safe offline reinforcement learning is formalized as a tuple, S, A, T, R, C, gamma, B, where S is the state space, A is the action space, T is the transition probability function, R and C are the reward and cost functions, gamma is the discount factor, and B is the safety budget. A policy pi maps states to a probability distribution over actions, with the goal of learning a policy that maximizes the expected cumulative reward while satisfying the cumulative cost constraint. In real-time budget constraints, the budget is dynamically determined, and the optimization objective is to maximize the expected cumulative reward for a given budget B, subject to the constraint that the cumulative cost does not exceed B. A naive solution is to discretize the budget range and train a separate policy for each discrete value, but this approach is computationally expensive and may not cover all possible budgets. The authors propose a solution based on planning with trajectory optimization, which provides flexibility for dynamic switching of constrained optimization objectives during real-time inference. This is achieved through the use of diffuser, a diffusion-based probabilistic model that can be used for trajectory optimization. In diffuser, raw data is converted into a noise distribution through a forward diffusion process, and the denoising process is used to progressively rebuild the data distribution from the noise distribution. Diffuser is used for trajectory optimization by training a denoising model to model the trajectory distribution of the behavior policy, and learning a function h to indicate the optimization objective. During inference, generated trajectories are guided for planning to achieve the optimization objective. This approach offers advantages over existing methods, such as state augmentation, by providing a flexible and efficient solution for safe offline reinforcement learning with real-time budget constraints. The section discusses the trajectory-based real-time budget inference, TREBI, for safe offline reinforcement learning. It begins by introducing a trajectory optimization perspective, where the policy optimization problem is converted into a trajectory optimization form. This involves maximizing the expected return under empirical dynamics while constraining the divergence between the target policy and the behavior policy. The in-distribution constraint is expressed as a KL divergence between the target trajectory distribution and the behavior policy's trajectory distribution. The policy optimization problem is then solved by maximizing the expected return subject to the in-distribution constraint. The section also presents a theorem ensuring the existence of an optimal trajectory distribution that satisfies the constraints. This distribution is obtained by zeroing the probability of unsafe trajectories and redistributing the probability of remaining trajectories based on their returns. A novel algorithm for safe offline reinforcement learning with real-time budget constraints is developed, leveraging a probabilistic graphical model to represent the likelihood of a given trajectory being optimal. This model approximates the true posterior distribution using an auxiliary trajectory distribution, which is optimized by minimizing the evidence lower bound, ELBO, through a two-phase trajectory optimization process. The proposed method employs the diffuser model to approximate the trajectory distribution and performs guided planning over the approximate distribution. To ensure safety, the algorithm adapts the guided planning of diffuser to the constrained setting by introducing a new trajectory distribution, Q** operator B, n, tau, which accounts for the budget constraints. This distribution is a product of the original trajectory distribution and a modified guiding function, hb, n, tau, dependent on the hyperparameter n controlling the conservativeness of the planning process. The optimization problem is formulated to find the optimal trajectory distribution within a feasible distribution family that satisfies the safety budget with probability 1. The solution to this optimization problem is shown to have a similar form to the original unconstrained solution, but with a tunable hyperparameter alpha that does not vary with the budget band divergence threshold epsilon. A practical algorithm, trajectory-based real-time budget inference, TREBI, is proposed to sample from the approximate optimal distribution Q** operator B, n. TREBI modifies the reverse process of the diffuser model by replacing the guiding function and gradient with their constrained counterparts, which take into account the budget constraints and the conservativeness level controlled by n. During inference, the algorithm iteratively updates the budget value B to ensure trajectories satisfy the corresponding constraints. The paper explores safe offline reinforcement learning with real-time budget constraints, delving into the theoretical analysis of the optimal trajectory distribution. It derives a performance guarantee for reward maximization and constraint satisfaction, emphasizing the significance of in-distribution constraints to mitigate dynamics inconsistency and uncertainty. Theoretical results, including Lemma 4.2 and Proposition 4.3, demonstrate the effectiveness of the approach in ensuring constraint satisfaction and maximizing rewards under budget constraints. This section provides a detailed explanation of the mathematical concepts and their practical implications, connecting theoretical analysis to algorithmic applications. In safety-critical environments, real-time budget constraints pose a significant challenge for reinforcement learning algorithms. To address this, researchers have developed a novel offline reinforcement learning algorithm, TREBI, which leverages a probabilistic approach to ensure that generated policies satisfy both in-distribution and safety constraints with high probability. TREBI's effectiveness is demonstrated through simulation experiments on various tasks, including OpenAI Gym, MuJoCo, and Bullet Safety Gym. The algorithm is compared against several baselines, including BCQ Lagrangian, CPQ, B-Coral, Lambda, and BCQ-SADE. The results show that TREBI outperforms these baselines in terms of constraint satisfaction and performance under different budgets. By incorporating a probabilistic approach, TREBI can efficiently handle real-time budget constraints, making it a promising solution for safety-critical applications. The algorithm's robust performance across various tasks and budgets highlights its potential for real-world deployment. The study's findings have significant implications for the development of reinforcement learning algorithms that can operate effectively in safety-critical environments, where real-time budget constraints are a critical concern. The paper discusses safe offline reinforcement learning with real-time budget constraints, introducing a novel approach called TREBI. TREBI efficiently utilizes datasets with varying quality to achieve high performance in trajectory constraint satisfaction. It outperforms baselines in terms of episodic reward and constraint violation, demonstrating its effectiveness under real-time budget constraints. The approach is demonstrated on various MuJoCo tasks, including pendulum, reacher, half-cheetah, and safety gym tasks, with promising results. The TREBI method is applied in a real-world advertising bidding scenario to optimize the cost per mil, OCPM, advertising bidding task. This involves maximizing the summation of the payments of all advertisers while satisfying the ROI constraint. The results of TREBI in this scenario show a total pay improvement relative to BCQ Lagrangian and a low violation rate, indicating the proportion of trajectories violating ROI constraints. This demonstrates TREBI's potential in solving the real-time budget constraint problem in real-world applications. Page 10 of the research paper presents a detailed compilation of the various methodologies and techniques employed in the study. This section serves as a reference guide for researchers, providing an overview of the tools and methods used to gather, analyze, and interpret data. The page begins by outlining the experimental design, which includes a description of the sample population, data collection procedures, and the statistical methods applied to identify patterns and trends within the dataset. It also delves into the theoretical frameworks that underpin the research, highlighting the conceptual lenses through which the findings are interpreted. A significant portion of the page is dedicated to the discussion of the data analysis techniques, including both qualitative and quantitative approaches. The authors provide a step-by-step explanation of how they processed and analyzed the data, including the software used and the specific statistical tests applied. This level of detail allows other researchers to replicate the study or apply similar methodologies in their own work. Furthermore, the page touches upon the ethical considerations that guided the research, emphasizing the importance of maintaining participant confidentiality and adhering to established guidelines for conducting research involving human subjects. This section serves as a reminder of the ethical responsibilities that researchers must uphold when conducting studies that involve human participants. In conclusion, page 10 of the research paper offers a valuable resource for researchers seeking to understand the methodologies and techniques used in the study. By providing a comprehensive overview of the experimental design, data analysis techniques, and ethical considerations, this section serves as a practical guide for those looking to conduct similar research in the future. The concept of safe offline reinforcement learning with real-time budget constraints is discussed, introducing the Coptitus algorithm. This algorithm uses stationary distribution correction estimation for offline constrained reinforcement learning, designed to operate within a budget constraint, ensuring a safe and efficient learning process. In the realm of offline reinforcement learning, ensuring safety while meeting real-time budget constraints is a paramount concern. The MOPO method, a model-based offline policy optimization approach, has been proposed to address this challenge. Building upon MOPO, the combo method introduces conservative offline model-based policy optimization, which prioritizes caution in decision-making. Another key technique in this context is first-order constrained optimization in policy space, which enables efficient policy optimization while satisfying constraints. Beyond these methods, researchers have explored the application of safe offline reinforcement learning in various domains. For instance, the BQoral framework has been developed for coupons allocation in e-commerce, where the goal is to maximize revenue while minimizing costs. Similarly, the DRN framework has been designed for news recommendation, aiming to balance user engagement with content diversity. These approaches collectively contribute to the advancement of safe offline reinforcement learning strategies, enabling the development of robust and efficient decision-making systems in real-world applications. Theorem A.1, a pivotal component of the proposed safe offline reinforcement learning framework with real-time budget constraints, states that if the cumulative cost function R_C, tau, lec b, pi underscore, beta, tau, d, tau, geq caret, epsilon, holds, there exists an optimal trajectory distribution for the problem defined by equations 21, 22, and 23. This problem aims to maximize the expected reward while adhering to a given budget constraint and maintaining a certain level of similarity between the trajectory distribution and the baseline policy. The optimal trajectory distribution, denoted as q_b, tau, has the form given in equation 24. It is composed of two parts. One where the cumulative cost function c, tau, lec b, and another where it does not meet this condition. The normalizer z ensures that q_b, tau, is a valid probability distribution. To prove theorem A.1, a lemma is first introduced, which addresses an optimization problem involving continuous variables x. The goal of this optimization problem is to minimize the objective function j, q, as defined in equation 25, subject to the constraint in equation 26. The solution to this optimization problem is provided by the Lagrange function L, x, q, dot, q, which leads to the Euler-Lagrange equation. Solving this equation yields the optimal solution q caret, x, equals p, x, int underscore ap, x, dx, where p, x, is a probability distribution and a is a subset of the domain x of x. This lemma is then used to prove theorem A.1. By applying the lemma to the original problem, we can derive the form of the optimal trajectory distribution q_b, tau. This distribution is essential for the proposed safe offline reinforcement learning framework, as it allows for the optimization of expected rewards within the constraints of the cumulative cost function and baseline policy similarity. In the safe offline reinforcement learning problem with real-time budget constraints, the authors provide a proof for the existence of a solution. They start by assuming that the probability of a constraint violating trajectory, PC, is arbitrarily close to 1. This allows them to avoid the occurrence of p, tau, equals 0 in the calculation of the KL divergence. As PC approaches 1, the probability of a constraint violating trajectory tends to 0, and the KL divergence between the distribution q, tau, and the behavior distribution ppb, tau, approaches 0. The authors then derive the trajectory distribution closest to the behavior distribution under the safety constraint, given by q** operator, tau, equals ppb, tau, if R_c, tau, is less than or equal to b, and 0 otherwise. The existence of a distribution q, tau, that satisfies both the safety constraint and the indistribution constraint is guaranteed only when the divergence between ppb, tau, and q** operator, tau, is less than e. This leads to the condition z_c, tau, is less than or equal to b ppbd tau is greater than or equal to e caret, e. To solve the optimization problem, the authors construct a Lagrange function L, tau, q, that incorporates the reward function, safety constraint, and indistribution constraint. By applying the Karish-Kuhn-Tucker conditions, they obtain the optimal distribution q** operator, tau, equals ppb, tau, express, alpha r, tau, z. If c, tau, is less than or equal to b, and 0 otherwise. This derivation provides a solution to the safe offline reinforcement learning problem with real-time budget constraints, ensuring that the learned policy satisfies both safety and indistribution constraints. The authors derive the relationship between Lagrangian multipliers lambda and micro, and variables z and alpha, using the KKT conditions. They obtain equations 30 and 31, describing constraints on the trajectory distribution q, tau, and the budget constraint b. Solving these equations, they arrive at the expression for z in terms of b, ppb, tau, and the reward function r, tau. Additionally, they derive the relationship between alpha, z, and the divergence threshold E. The authors then shift their focus to the probabilistic inference perspective, aiming to minimize the discrepancy between the auxiliary trajectory distribution Q, tau, and the optimal trajectory distribution of the behavior policy PPB, tau, O equals 1. They derive the ELBO objective, equivalent to maximizing the function j, q, tau, where j, q, tau, equals dkl, q, tau, p1, tau, and p1, tau, is a modified version of the behavior policy. The authors reformulate the optimization problem from the probabilistic inference perspective, involving maximizing j, q, tau, subject to the constraint that the expected cost of the trajectory distribution does not exceed the budget B. By applying lemma A.2, they obtain the optimal trajectory distribution Q** operator, tau, which has the same form as the one derived earlier, but with a preset hyperparameter alpha. The authors highlight the difference between alpha and alpha, where alpha controls the degree of policy improvement and is determined by the divergence threshold E and budget B, whereas alpha is a preset hyperparameter independent of E and B. This difference arises because the indistribution constraint is not present in the probabilistic inference process. The authors delve into the proof of lemma 4.2 and proposition 4.3, which are crucial in establishing the theoretical foundations of safe offline reinforcement learning with real-time budget constraints. They introduce notations for the expected return of a policy pi under the environment with transition dynamics T, denoted as JT, pi. The empirical behavior policy, transition dynamics, reward function, and cost function, estimated from the offline dataset, are defined as PB, T, R, and C, respectively. The learned policy pi and transition dynamics TQ, induced from the trajectory distribution Q, tau, are presented using equations 33. For simplicity, the authors ignore the sampling error of the reward function and focus on the sampling error of the cost function, which is critical in constrained problems. In lemma A.3, restated from the main paper, the authors bound the gap between the expected returns of the policy pi under the real environment T and the empirical dynamics T. The bound is given by equation 34, consisting of two terms. The first term vanishes in deterministic environments, and the second term represents the error due to the difference in cost functions. Assumption A.4 is then introduced, assuming concentration properties for the transition dynamics and cost function. This assumption is used to derive a modified lemma, lemma A.5, which bounds the return gap between two policies in different environments. Lemma A.5 is a modified version of lemma B.3 from Janner et al. 2019, and provides an upper bound on the difference in expected returns between two policies in different environments. The bound is given by equation 35, involving the total variation distance between the transition dynamics and policies of the two environments. These results lay the foundation for the subsequent proofs and analyses in the paper, providing a theoretical guarantee for the safe offline reinforcement learning algorithm. Safe offline reinforcement learning with real-time budget constraints necessitates controlling trajectory divergence between two policies, pi1 and pi2, under their respective induced state action visitation distributions, PT1 and PT2. The authors establish bounds on this divergence using a series of lemmas and proofs. Central to this analysis is the relationship between the Kullback-Leibler (KL) divergence of the trajectory distributions, DKL, P1, tau, P2, tau, and the divergence of the state and state action visitation distributions, DTV, P1, S, A, P2, S, A, and DTV, pi1, S, pi2, S, respectively. Lemma A.6 states that if the KL divergence between the trajectory distributions P1, tau, and P2, tau, is bounded by epsilon, then the divergence of the state and state action visitation distributions is also bounded. The authors prove this lemma using the definition of the KL divergence and Jensen's inequality to obtain a lower bound on the KL divergence in terms of the divergences of the state and state action visitation distributions. Subsequently, the authors prove lemma A.3, which pertains to the return gap between two policies, pi1 and pi2, under their respective induced dynamics, T1 and T2. The return gap is defined as the difference in the expected cumulative rewards obtained by following these policies in their respective environments. In deterministic dynamics, the return gap is zero due to the consistency of the dynamics models T1 and T2. However, in probabilistic dynamics, the return gap is non-zero and depends on the trajectory divergence between the empirical behavior and target behavior policies. By bounding the divergence of the state and state action visitation distributions, the authors aim to guarantee that the learned policy will not deviate significantly from the target policy during deployment, thereby ensuring safety and efficiency in the reinforcement learning process. Controlling trajectory divergence is crucial for safe offline reinforcement learning with real-time budget constraints. The authors continue to develop their safe offline reinforcement learning framework, focusing on the return gap and uncertainty return gap between the true and learned transition models. They begin by bounding the return gap between the true and learned transition models, denoted as JTQ, pi, and JT, pi, respectively. This is achieved by applying the Pinsker inequality and the triangle inequality, resulting in equation 41, which shows that the return gap is upperbounded by a term involving the radius of the model class, the discount factor, and the uncertainty tolerance. Next, the authors consider the return gap between the behavior policy pi and the learned policy pi, denoted as JT, pi, and JT, pi, respectively. They derive an upper bound for this gap, given in equation 45, which involves the cumulative uncertainty reward of the learned policy and the behavior policy. The authors then combine the two bounds to obtain a final bound on the return gap between the true and learned transition models, given in equation 47. This bound consists of two terms. The first term vanishes in deterministic dynamics, and the second term represents the cumulative uncertainty reward of the learned policy. Finally, the authors focus on the uncertainty return gap between the behavior policy and the learned policy, denoted as UT, pi, and UT, PB, respectively. They derive an upper bound for this gap, given in equation 49, which involves the cumulative uncertainty reward of the learned policy and the behavior policy, and is upperbounded by a term involving the radius of the model class, the discount factor, and the uncertainty tolerance. The concept of safe offline reinforcement learning with real-time budget constraints is discussed, starting with bounding the return gap between the estimated and true environments. This is achieved by utilizing the upper bound of UT, pi, to derive an error bound for the return gap in equation 52. The error bound is further broken down into two components in equation 54, with one component vanishing in deterministic dynamics. The paper then proves proposition A.7, stating that for any policy pi derived from a trajectory distribution satisfying both the indistribution constraint and safety constraint, there exists an inequality with probability at least 1 delta. This inequality, given in equation 55, relates the expected cumulative reward of the policy pi q asterisk operator b induced by the constrained optimal trajectory distribution q asterisk operator b to the expected cumulative reward of the policy pi. The first term in the inequality, 1 gamma L plus 1 QLE, 2, vanishes in deterministic environments. Additionally, the paper proves that for each trajectory tau generated from q asterisk operator b, the episodic cost of tau is bounded with probability at least 1 delta, as shown in equation 56. This bound is obtained using the concentration properties and the fact that the empirical cost can be accurately modeled in TQ under the assumption made in the paper. Simulation environments and datasets for safe offline reinforcement learning with real-time budget constraints are presented. The pendulum and reacher tasks require an agent to balance a pendulum or control a robotic arm while avoiding unsafe regions, with cost functions defining a trade-off between task objectives and safety constraints. Mu-Jo co-environments involve controlling robots to maintain balance and move forward with minimal velocity cost. 3 types of offline datasets from D4RL are utilized for each environment. The bullet safety gym environments, including safety car circle and safety ball reach tasks, require the agent to navigate within a safety zone or avoid collisions with obstacles. Offline datasets are collected by training an unconstrained SAC policy online and taking its replay buffer as the dataset. The relationship between reward and cost is explored, demonstrating that stricter constraints lead to lower rewards due to the conflict between task objectives and safety constraints. This results in the optimal solution being located at the edge of the feasible policy space, which may shrink when constraints are tightened. A real-world advertising bidding scenario is also presented, where the system must ensure that the average conversion meets or exceeds the target ROI while staying within the maximum total pay. This is achieved through a bidding process where the system allocates pays, T for advertiser S, ensuring that the total expenditure does not exceed the maximum pay and the target ROI is met. In the realm of real-time bidding, the optimization problem is framed as maximizing total pay while adhering to budget constraints. This scenario is modeled using a Markov decision process, MDP, where the state encompasses user and ads context features, cumulative revenue, and other pertinent metrics. The action taken is the output of a bidding weight, with the reward being the pay for a successful bid. The constraint in this MDP is the budget, which carries a negative connotation, indicating it needs to be satisfied over time. To deploy this model effectively, the state must be modified to include the remaining budget, and a high reward should be assigned for reaching the target cumulative gross merchandise volume. Data collection is facilitated by a set of constrained policies, which are then implemented using the diffuser framework. This requires components for mean modeling, reward estimation, and cost estimation to function optimally. This approach ensures that the bidding strategy not only maximizes pay but also respects the budget constraints, thereby enhancing overall efficiency in real-time bidding scenarios. The implementation details of TREBI, a safe offline reinforcement learning algorithm, are presented, focusing on its performance under real-time budget constraints. Evaluations on tasks like pendulum, reacher, mu-joko, and bullet safety gym demonstrate TREBI's superior performance in constraint satisfaction and overall returns compared to baseline algorithms. Additional results on Hopper and Walker 2D datasets show nearly perfect constraint satisfaction with high budget ratios. However, the algorithm struggles with low budget ratios due to the limited availability of constraint-satisfying samples in the dataset. This is in line with Theorem 4.1 regarding dataset quality, highlighting implications for future research. The paper delves into the realm of safe offline reinforcement learning, a paradigm that operates under real-time budget constraints. It presents empirical results on two tasks, Hopper and Walker 2D, which underscore the significance of control frequency in maintaining performance while reducing computational costs. The analysis reveals that decreasing the control frequency from per 1 step to per 4 step leads to a slight decline in rewards but insignificantly affects constraint violations. This suggests an optimal balance between performance and efficiency, where computational costs are minimized without compromising the overall performance of the reinforcement learning algorithm. In essence, this study contributes to the understanding of how control frequency can be adjusted to achieve a trade-off between computational efficiency and task performance in safe offline reinforcement learning settings. The findings have implications for researchers seeking to deploy reinforcement learning algorithms in real-world scenarios where computational resources are limited and time-sensitive decisions need to be made. TREBI's performance in various environments under different budget constraints is a key focus of this analysis. Consistency across budget levels in both mu-joko and bullet safety gym tasks is consistently demonstrated by TREBI, as shown in figures 811. These results highlight the effectiveness of TREBI under randomly selected budgets, showcasing its adaptability and efficiency in resource-constrained scenarios. In contrast, fixed budget baselines such as BCQ Lagrangian and CPQ were not evaluated under these settings due to the computational requirements of retraining for each new budget. This limitation underscores the importance of TREBI's ability to adapt and perform well without the need for extensive retraining, making it a more practical solution for real-world applications where budgets can fluctuate. The use of TREBI in these experiments allows for a comprehensive understanding of its capabilities and limitations, particularly when compared to other state-of-the-art methods. By examining its performance under varying budget constraints, Researchers can better understand how to optimize the use of TREBI in different scenarios and environments. Overall, the results presented in this section emphasize the versatility and reliability of TREBI, even in situations where budgets are unpredictable or variable. This information is crucial for researchers and practitioners looking to implement efficient and adaptable reinforcement learning algorithms in their work. The results of experiments on half-cheetah and hopper tasks with random budgets sampled from 0, 1 are presented in figures 8 and 9, respectively. Each figure illustrates the cost and reward under different budgets, where the z-axis represents the given budget as a fraction of the maximum budget. These figures demonstrate the effectiveness of the proposed safe offline reinforcement learning algorithm in navigating the trade-off between cost and reward under real-time budget constraints. The algorithm is able to adapt to different budgets and achieve high rewards while respecting the cost constraints. The results are presented in a tabular format, with each row representing a different budget level. The columns represent the cost and reward achieved by the algorithm under each budget level. The tables also include confidence intervals for the results, indicating the variability of the outcomes. The page also includes mathematical notation and equations, which are used to describe the algorithm and its components. Specifically, the notation includes symbols for the state and action spaces, the reward function, and the cost function. The equations describe the optimization problem solved by the algorithm, which involves maximizing the reward while respecting the cost constraints. Overall, the page provides a detailed presentation of the experimental results and mathematical formulation of the safe offline reinforcement learning algorithm, highlighting its ability to effectively navigate the trade-off between cost and reward under real-time budget constraints. Applying safe offline reinforcement learning with real-time budget constraints to Walker 2D and bullet safety gym tasks yields promising results. The algorithm adapts to changing budgets, achieving optimal performance in both tasks. In the Walker 2D task, the algorithm's performance is evaluated under varying budget constraints, ranging from 0.1 to 1.0. The results, presented in Figure 1, demonstrate a significant improvement in the cumulative reward as the budget increases. Notably, the algorithm's ability to adapt to changing budgets is evident, as it achieves near-optimal performance even with limited budgets. The bullet safety gym task presents a more complex environment, with the algorithm required to navigate safety constraints while optimizing performance. The results, shown in Table 1, highlight the algorithm's capacity to balance safety and performance under varying budget constraints. Specifically, the algorithm achieves a high success rate in avoiding safety violations while maintaining a high cumulative reward. The key takeaway from these results is the algorithm's flexibility in adapting to real-time budget constraints, ensuring optimal performance in both tasks. This is particularly significant in real-world applications, where budget constraints often change dynamically. The results also underscore the importance of considering safety constraints in reinforcement learning, as the algorithm's ability to navigate these constraints is critical to achieving optimal performance. Future work may involve exploring the applicability of this algorithm to more complex tasks and environments, as well as investigating the impact of varying safety constraints on performance.